Good morning, students. So today we are again here for the fourth lecture on revision of differential equations. So earlier we discussed variable separable methods, homogeneous differential equations, we discussed linear differential equations, exact differential equations and differential equations of the form f of x, y, p is equal to 0. And the last topic which we covered was Clairaut's differential equation. Now we move towards the next topic, that is linear differential equations with constant coefficients. In this chapter we will denote ddx by capital D, and if an equation, suppose it is d2y by dx2 plus 3 dy by dx plus 2y is some function of x, then as I said earlier, ddx will be denoted by d. The second derivative d2x by dx2 will be denoted by d square. d3 upon dx3 will be denoted by d cube, and so on. So what this equation will look like? It will look like d square y plus 3 dy plus 2y is equal to fx. That means you can say d2 plus 3d plus 2y is equal to fx, and we will call this equation in symbolic form. This equation is in symbolic form, and this thing, that is d2 plus 3d plus 2, if we equate it to 0, then it will be an equation in D and will be called auxiliary equation. It will be called auxiliary equation, and we will denote it by AE. Now this equation, we can find roots of this equation too. So suppose I factorize this as d plus 1, d plus 2 is equal to 0. I will obtain roots as minus 1 and minus 2. On the basis of these roots, we can find complementary function, of the given differential equation, and again in short we will denote it by CF. And there will be the second part. This is one part of the solution of the differential equation, and the other part of the differential equation will be called particular integral. So particular integral, again we use the short form pi, will be equal to 1 upon this function of d square plus 3d plus 2 of the function on the right hand side, that is fx. And we will have some techniques to evaluate this particular integral, to find this complementary function. After obtaining complementary function and particular integral, the complete solution, again in short we denote it by CS. The complete solution will be given by y is equal to CF plus PI. That means CF will be a part of the final solution, and particular integral PI will be the other part of the solution of the differential equation, and the complete solution of the differential equation will be given by y is equal to CF plus PI. Now the question is how to find CF and how to find PI. We will take this step by step. First we will learn how to find CF, that means the complementary function of a differential equation which is given in this form. So suppose I am having some linear differential equation with constant coefficients. I obtained the auxiliary equation. I obtained the roots of the auxiliary equation. Now, depending on the nature of roots of auxiliary equation, how CF will look like. Suppose alpha, beta, gamma, delta and so on. These are the roots of the auxiliary equation. If these are all real and distinct, these are all real and distinct, then complementary function of this differential equation will be C1 e raised to the power alpha x plus C2 e raised to the power beta x plus C3 e raised to the power gamma x plus C4 e raised to the power delta x plus and so on, where these coefficients C1, C2, C3 and C4 can be obtained if some boundary conditions are given. Normally, in such differential equations, boundary conditions are not given, so this CF will be in its final form, in its final look. This is one type where the roots are real and distinct. What if the roots are real but not distinct? Suppose a root alpha occurs 3 times, alpha, alpha, alpha. Another root beta occurs 2 times, and then gamma, delta and so on. Some other roots are also there. Then this CF, the complementary function, will look like this alpha. The part of the complementary function for this root alpha, which is repeated and has a multiplicity 3, will be C1 plus C2x plus C3x square into e raised to the power alpha x. This is the part of the complementary function due to this root alpha whose multiplicity is 3. Now plus this root beta is occurring here 2 times, its multiplicity is 2. So the part of the complementary function due to beta will be C4 plus C5x into e raised to the power beta x plus. Now these gamma, delta, etc., these are the simple roots with multiplicity 1 only, they are distinct roots. So their role will be again like that was in the first part. So we will get C5 was here, so we will have now C6 e raised to the power gamma x plus C7 e raised to the power delta x plus and so on. So these are the cases if the roots are real, but always the roots may not be real. Sometimes the roots are not real. So if the coefficients are real, then we know that the complex roots always occur in conjugate pairs. Since the coefficients are real, this is given to us, that means if complex roots are there, they will definitely be in conjugate pair. So maybe the complex conjugate pairs of the roots are simple, that means are having multiplicity 1 only. So we'll take a simple case. Suppose the roots are alpha plus minus iota beta and rest of the roots gamma, delta, etc., they are real and distinct. So how the complementary function will look like? Now this is alpha plus minus iota beta, 2 roots, they are complex conjugate of each other. The part of the complementary function due to these 2 roots will be e raised to the power alpha x. In the bracket you will have C1 sin beta x plus C2 cos beta x. Now since the rest of the roots are simple, so what you will get for gamma? You will get C3 e raised to the power gamma x, C4 e raised to the power delta x plus and so on if more roots are there. It may happen that the complex conjugate pairs of the roots are also not simple. They do have multiplicity. So take up another case. If these roots are also occurring more than 1 times, suppose alpha plus iota beta is having multiplicity 2 There may be simple roots, real roots also with multiplicity, maybe gamma 3 times, maybe delta 1 time, and so on. Then what will be your complementary function? The part for this alpha plus iota beta and alpha minus iota beta, these two roots have multiplicity 2. So what they will look like? It will be e raised to the power alpha x. In place of c1, you will have c1 plus c2x sine beta x. Similarly, for c2, you will have c3 plus c4x cos beta x plus. Now, gamma is also occurring 3 times. It is a real root. So, what will be? It will be c5 plus c6x plus c7x square and e raised to the power gamma x plus delta is a simple root occurring once only, so you will get ca e raised to the power delta x plus if more roots are there. So these are the all possible cases of roots of the auxiliary equation. So it is clear how to find the complementary function for a linear differential equation with constant coefficients. If the right hand side of the differential equation is 0, then clearly there will be no integral part and the complementary function will be the complete solution of the differential equation. Let us discuss a case. So I am taking up a differential equation and suppose the differential equation which is linear and with constant coefficients be d square plus 7d plus 6 y is equal to 0. Here I have taken right hand side the function of x to be 0. That means the particular integral will be 0. There will be no particular integral. Only complementary function will be there and that will be the complete solution of the differential equation. First of all, we will find the auxiliary equation. The auxiliary equation in this case is d square plus 7d plus 6 is equal to 0 and the factors of this equation are d plus 1, d plus 6 is equal to 0 giving d is equal to minus 1 and minus 6. So we are having two roots which are real and distinct. So what will be the complementary function of? So the complementary function will be the first case of the previously discussed complementary functions for different cases of roots of the auxiliary equation. We will have c1 e raised to the power minus 1x plus c2 e raised to the power minus 6x and the complete solution of given differential equation will be y is equal to cf only because there is no particular integral, the right hand side of the equation being 0. So the solution will be y is equal to c1 e raised to the power minus x plus c2 e raised to the power minus 6x. That will be the solution. So I think you have now understood how to find the complementary function of a given differential equation with constant coefficients. The thing is how to find the particular integral. The computation, the evaluation of the particular integral depends upon the function on the right hand side. It may be an exponential function, it may be a trigonometrical function, it may be some power of x, it may be the combination of these various functions. So in different cases, the particular integral will be different. We will discuss these cases one by one. So let us first take the case when the function on the right hand side is an exponential function. That means your equation is something like fd y is equal to e raised to the power ax. If your differential equation looks like this, the particular integral as discussed earlier will be 1 upon fd e raised to the power ax. Since it is revision class, I am not going to directly tell you how to find it. The method is just substitute the value of coefficient of x in the power of exponential in place of d, and you will get the solution. So that will be equal to 1 upon fa e raised to the power ax. The condition is that fa should not be 0. F of a should not be 0. That means, suppose you are having 1 upon d square plus 5d plus 1 e raised to the power minus 3x. So what it will be equal to? It will be equal to 1 upon the coefficient of x in exponential is minus 3. So just you have to replace d by minus 3 here. So what you will get? Minus 3 square plus 5 into minus 3 plus 1 e raised to the power minus 3x is equal to 1 upon, now solve it. It is 9 plus 1, 10 minus 15 is minus 5. So minus 5 e raised to the power minus 3x. That means minus e raised to the power minus 3x over 5 is the particular integral in this particular case. But this is only then when f of a is not 0. What happens if f of a is 0? So it is the next case. If f of a is 0, if f of a happens to be equal to 0, then this method will not work, because 1 upon 0 will be ambiguous quantity. So we will not go through this case. What we have to do then? Then we will write this as, after this term, we are going to write it equal to, we will write x here, and then 1 upon derivative of this with respect to d, derivative of fd with respect to d, and e raised to the power ax. Again, provided f dash d, sorry, here it is not the case. Now how to deal this one? Earlier we were having fd, so fa was 0, so we will have to adopt this rule. Now again we are to proceed as in the earlier case. We will replace d by a again, so it will become 1 upon f dash a e raised to the power ax, again provided f dash a is not equal to 0. Once again, if f dash a happens to be 0, if f dash a also happens to be 0, further this term will go to 1x was there, 1 more x will come outside, so you will get x square, 1 upon, it was f dash d, and now you will get the second derivative f double d dash d of e raised to the power ax, and once again the same thing, this x square is as it is, replace this d by a, so 1 upon f double dash a e raised to the power ax, again provided f double dash a is not equal to 0, and continue like this, you will get the particular integral, and the complete solution will be y is equal to cf plus pi. So let us take a case. We will take 2 or 3 differential equations with constant coefficients to discuss such a case in detail. So first I am taking I am taking the equation d2y by dx2 plus y is equal to e raised to the power 3x. Look into this equation. First of all, in the symbolic form, it will become d2 plus 1 y is equal to e raised to the power 3x. It is in the symbolic form. Now, its auxiliary equation. The auxiliary equation will be d square plus 1 is equal to 0. And you know that roots of this equation are d is equal to plus minus iota. You can say 0 plus minus 1 iota. So alpha plus minus iota beta, that means the complex roots and conjugate pairs. So what will be the solution? What will be the complementary function? So complementary function will be e raised to the power alpha x, that means 0x, c C1 sin 1x, beta is 1, plus C2 cos 1x. E power 0x is e power 0, that means 1. So you will left with C1 sin x plus C2 cos x. This will be the complementary function. And what will be the particular integral? Particular integral will be 1 upon d square plus 1 e raised to the power 3x. And as we discussed earlier, what we have to do? Just replace d by 3. So you will get 1 upon 3 square plus 1 e raised to the power 3x. That means e raised to the power 3x upon 10. This is the particular integral. Now the complete solution is y is equal to cf plus pi. That means y is equal to, this was your cf, c1 sin x plus c2 cos x plus pi is e raised to the power 3x by 10. This is the complete solution. And further, if two boundary conditions are given, then by substituting the values of x and y from the boundary conditions, we will get two linear equations in C1 and C2, from where we can yield the values of C1 and C2. Substituting the values of C1 and C2, we will get the final solution of this differential equation. This is the case when f of a was not 0. Let us take up one more case. I am considering another differential equation, linear differential equation with constant coefficients. Suppose my equation is d square plus 4d plus 3y is equal to e raised to the power minus 3x. Let us take with this equation. Similarly, as we did in the first case, first of all, the auxiliary equation. So auxiliary equation is d square plus 4d plus 3 is equal to 0. The factors will be d plus 1, d plus 3 is equal to 0. The roots of the auxiliary equations will be minus 1 and minus 3. So the complementary function part will be c1 e raised to the power minus x plus c2 e raised to the power minus 3x. Now we move on to the particular integral. Particular integral will be 1 upon fd. Your fd here is d square plus 4d plus 3, and on the right hand side you will have this function e raised to the power minus 3x. So what we have to do now? We have to substitute this d by minus 3. But if you substitute this d by minus 3, what you are going to get? You will get minus 3 square plus 4 into minus 3 plus 3, which is equal to 0. So it is a case of failure. So in case of failure, what we have to do? How we have to proceed further? What we have to do? We will write x here and then 1 upon, we will differentiate this with respect to d. So derivative of d square is 2d plus derivative of 4d is 4, derivative of 3 is 0, and e raised to the power minus 3x. Once again, substitute d by minus 3. So you are going to get x into 1 upon 2 into minus 3 plus 4 e raised to the power minus 3x, or you can say minus x e raised to the power minus 3x upon 2. This is your particular integral. This was your CF, this is your particular integral pi. So what will be the complete solution? Complete solution will be y is equal to cf plus pi. That means y is equal to c1 e power minus x plus c2 e raised to the power minus 3x plus the particular integral, which is minus x e raised to the power minus 3x upon 2. So this is the final solution of this differential equation. So we discussed the case when our function is exponential function. This is one method. Now we move on to the second method, when our function is a trigonometric function, sin x or cos x. So this is a particular case, sin x and cos x. For tan x, secant x, cosecant x and cotangent x, we will have different procedures, different technique. So how to proceed if you are having f of dy is equal to sine of ax or cos of ax, the technique is similar, same. There is no difference if there is sine or if there is cos. How to proceed? How to find complementary function is the same procedure as in earlier cases. The only difference is the procedure to find the particular integral. So particular integral in this case will be 1 upon fd sine of ax. In case of exponential function, what we did, we replaced d by a, and if f of a is not equal to 0, we obtained the particular integral. If f of a is 0, then the method was different. Here, if your function is sine ax or cos ax, the same cases, the similar cases, what we will do, what we are to do, we will replace d square by minus a square in f of d. And if you come to a result with f of minus a square replacing d square by minus a square, if it is not 0, you will be with the final solution. If it comes out to be 0, the procedure is similar. In that case, what you have to do, you will write it as x 1 upon f dash d sine of ax, and once again you will replace d square by minus a square in f dash d. If the denominator is non-zero, you will get the solution. If it is 0, again you will have x square and one more times derivative, and again replace d square by minus a square. If it is not 0, you are going to get the particular integral, and so on. Now, we discuss some cases. We are going to illustrate some examples to evaluate particular integral in such case. Suppose your equation is d square plus 3d plus 2y is equal to sine 3x. Suppose this is your question. You know auxiliary equation. The roots of the auxiliary equation will be minus 1 and minus 2, and your complementary function will be c1 e raised to the power minus x plus c2 e raised to the power minus 2x. This will be your complementary function, where we are to concentrate on the particular integral. Particular integral will be 1 upon d square plus 3d plus 2 sine of 3x. What is a here? A is 3. And I asked you to replace d square by minus a square. A square means 3 square. So that means minus 9. Replace d square by minus 9. So what you are going to get is 1 upon this d square will become minus 9 plus 3d plus 2 sine 3x, or you can say 1 upon 3d minus 7 sine 3x. Now we are left with no d square or power of d square in the denominator. There is only one d. So how to convert this d into d square? We will have to multiply the numerator and denominator by 3d plus 7. That means some sort of rationalization, you can say. So multiply this part, the numerator as well as denominator, by 3d plus 7. What you are going to get? 3d plus 7 over, in the denominator you will get 9d square minus 49 sine 3x. Now you know what to do. In the denominator you have to replace this d square by minus 9. So minus 9 into 9 is minus 81. Minus 81 and minus 49 is minus 130. So you will get minus 1 upon 130 3d plus 7 and sine 3x. Now open this bracket. You will get minus 1 upon 130 3 d of sine 3x. d of sine 3x. d of sine 3x means derivative of sine 3x. And derivative of sine 3x is 3 cos 3x. So 3 cos 3x into 3 is 9 cos 3x. This is 9 cos 3x plus this 7 into sine 3x. This is now your particular integral. And what the complete solution is? Complete solution will be y is equal to cf plus pi. So here it is your cf and here it is your pi. So just you have to write y is equal to cf plus pi. Cf means c1 e power minus x plus c2 e raised to power minus 2x plus pi means minus 1 upon 130 9 cos 3x plus 7 sin 3x. So this will be the final solution of this differential equation. Now we take up one case of failure. How to proceed if f of d square becomes 0. So I'll take up some simple example. Suppose the given differential equation is d square plus 4y is equal to cos 2x. Auxiliary equation, you know, d square plus 4 is equal to 0. Its roots are clearly plus minus 2 iota. That means 0 plus minus 2 iota. So what will be the complementary function? c1 sin 2x plus c2 cos 2x. c1 sin 2x plus c2 cos 2x. This will be your complementary function of the final solution part, that is due to complementary function. Now, what is particular integral? Particular integral is 1 upon d square plus 4 cos 2x. What our job is to replace d square by minus a square. What is a here? A is 2. So we have replaced d square by minus 2 square, that means minus 4. So it will be minus 4 plus 4 is 0. So it is a case of failure. In case of failure, what we have to do? We will write x here and then we will differentiate every term in the denominator with respect to d. So derivative of d square is 2d and derivative of 4 we know is 0. So it is cos of 2x. There is no d square or power of d square in the denominator. To make it d square of power of d square, what we have to do? Multiply the denominator and numerator by d. So if you multiply the numerator by d, you will get d here and you will get d square here. Now once again you are having d square in the denominator. So what you have to do? Replace d square by minus 4. So replace this d square by minus 4. You will get minus x by 8 d of cos 2x. And d of cos 2x means derivative of cos 2x. And derivative of cos 2x is minus 2 sin 2x. So you will get x upon 4 sin 2x. So this is your particular integral. So the complete solution is y is equal to cf plus pi. That means y is equal to c1 sin 2x plus c2 cos 2x plus x upon 4 sin 2x. For your convenience, you can combine these two by taking sin 2x common. So what you will get? You will get y is equal to c1 plus x upon 4 sin 2x plus c2 cos 2x. So I am stopping the video here. So you will discuss 3 cases: how to find complementary function, how to find particular integral if your function is exponential, or trigonometric functions of sine or cosine. So in the next video we will discuss how to find the particular integral if the right hand side is some power of x, or it is a combination of some power of x, e power x, exponential function, or trigonometric functions of sine and cosines. So once again, I would like to thank in advance for your liking, for your sharing, for your subscribing this channel. Thank you once again. be attached with me for such videos on differential equations, on topology, on various other topics of mathematics, as well as amazing knowledge of mathematics and non-mathematical world. Thank you.